Hey everyone, how are y'all doing? Great, that was an amazing answer, you guys. One more time, how are we doing today? Good. Are you guys excited for SwRI? Yes, good. Okay. So just like normal, we're going to go through a few quick announcements. If you haven't signed in already, go ahead and scan that QR code. The tiny URL will also be on the other slides in case you don't get a chance to do it right now. So we're using Slido, so if you haven't used this before, it's essentially a Q&A forum that's online. So if you're streaming with us today, or if you just want to ask a question but not out loud, you can go to sli.do and do the room code SwRI, and you can put in your questions there. Member dues, if you haven't paid your dues, there's two ways to do it. Number one, you can go to acm-utsa.org/join, and you can also scan this code right here, and that'll take you directly there. Or you can pay in cash, and you can flag down Lauren Dill. She's in the back right there. She's waving. And those are the two ways you can pay dues. Yes, absolutely, yes. So even if you're not a member, you're totally allowed to come to meetings. It's just if you want to be a full-fledged member where you get a t-shirt and get to participate in some extra stuff. Slack is our main platform for communication. So who in here is not on Slack right now? Great. Okay, one person. Okay, we'll get you on there. So to join the workspace, you can pay your dues online and you'll get an invitation sent to your email. You can pay in cash and we'll send you an email, or you can just talk to an officer and we'll make sure that you get hooked up. In Slack, we have a few channels we just want to draw your attention to. So hackathons, careers, and opportunities, they're all pretty self-explanatory for the most part, but these three channels don't come like default equipped whenever you get into Slack for the first time. So I definitely recommend checking them out. And we have a ton of social media. So we have our YouTube channel, which is currently streaming right now, and you can go back and look at historical videos. Our Instagram, Twitter, Facebook, and LinkedIn, I would definitely recommend following us. We just want to be your friend. And our loyalty program, so 1 point for every ACM and ACMW general meeting, any workshops or socials, anything that we advertise like that. And then larger events like Rowdy Hacks or anything that we classify as a major event at some point is going to be 2 points. At the end of the semester, if you're returning next year and you're going to be in ACM again, we'll waive your fees. And if you're a graduating senior, you'll get an ACM stole, so you can walk to the stage with an ACM stole. Shirts, if you haven't gotten it yet and you are a full-fledged paying member, we have them. Just come talk to us after the meeting. And upcoming events. So tomorrow, ACMW is having Frost come in to talk about UX. That's going to be at 1 p.m. in Willow. That's right next door. And then we'll also have Frost staying with us a little bit later to talk about API security. So that's going to be at 5:30, and that's in the Mesquite room. So that's kind of over on the other side of the student union. It's like that way and then that way. Oh, it's in Willow? Oh, my bad. Okay, so it's in Willow apparently. So scratch that, not Mesquite, Willow. Okay, so if I have this correct, Frost UX, tomorrow 1 p.m., Mesquite, yes? And then API security, Frost again, 5:30 in Willow. Awesome. Man, our communication here, whew. Yes, okay, thank you. So trust technology, don't trust us. Rowdy Creators is meeting on Fridays at 10 a.m. That's in Hidalgo this week. ICPC meets on Saturdays at 10 a.m. That's always in the activity room, NPP 4.140. And we have, after we come back from the break, we have an underclassmen meeting. So this is expanding your dev environment on Git. So a lot of people that whenever they kind of get first started, they don't really know what Git is or anything like that. They just kind of like start going with it. So if you're an underclassman and you want to get a little bit of ahead of the curve before you get to like application programming, for example, then I would definitely recommend going to this so you can get a little bit more information on that. But that's going to be not next Monday, but the following Monday, March 16th at 1 p.m., and that's in the activity room. And then the following Wednesday, so March 18th at 1 p.m., we'll be in Mesquite, and we're going to be talking about cloud infrastructure. In fact, Joseph Roca is going to be talking about cloud infrastructure for Rowdy Hacks. Can you wave in the back there? Yes, he loves the attention, you guys. He loves it. So yeah, he'll be talking about that. So if you're interested in how we kind of like put that together for Rowdy Hacks, he'll be talking about that. Grace Hopper celebration, so application closes today. So if you have any sort of aspiration to go to Grace Hopper, I would definitely recommend just putting in the application. It doesn't hurt. and there's more information in the opportunities channel for that. Rowdy Hacks 2020, so March 28th and 29th, we're going to advertise this all the time. So that's a Saturday and Sunday. It's here on the main campus, HB Student Union. It's 100% free. Leon, do you have to be a seasoned programmer to go to this event? No, you do not. Absolutely, that's correct. So any skill level whatsoever, it doesn't matter if you're a CS major or CE or business or art, we want everybody there. So applications are now open. Go to rowdyhacks.io. You can fill out the application and follow us on social media. All right, so that's all the announcements. So without further ado, let's go ahead and welcome up SwRI to come talk about wrong way driver detection. Let's give it up.
All right. So how's everyone doing today? I think that was slightly more enthusiastic than the response you get. I'm going to take the win. All right, so Sabrina and I are coming back to our alma mater to come and talk to you all a little bit about what we're doing over at Southwest Research. So some of us graduated a little longer ago than others. It's actually funny, the last time I spoke in this room, I was SIing for a Texas history class about a decade ago. So it's kind of weird. It looks a little different than last time I was here. There wasn't all the lights and all the cool colors and stuff, so I like it. Progress, right? So today we're going to talk about wrong way driver detection, and we're going to talk about the technologies that were leveraged in getting from nothing to something that's useful to our end clients, which are transportation agencies. And Sabrina and I are going to be trading off throughout this, so she'll come up and talk for a while. Don't worry, she didn't kick me off. I actually invited her to come and talk for a little bit. So ITS is Intelligent Transportation Systems. What this is a concept of all of the technology that goes behind making highways work, whether that be for state departments of transportation, cities like San Antonio, or counties like Bexar County. All these agencies own roadways and need to leverage technology in order to make those roadways work more efficiently. The alternative is to build tons and tons more roads and fill more and more space, which is cost prohibitive and space prohibitive as well. So we need to use technology to get more out of the existing roadways and, when needed, build new roadways. We've been doing this for a while. We started working with TxDOT back in '98, so 22 years ago now. And at that point, we were doing advanced traffic management systems, which we are still doing today, and we're now in 13 states across the nation and growing. We actually just picked up a new state last month. What we do in that environment is we interface with all of the technology that's out there on the roadways, your traffic cameras, your vehicle sensors, weather sensors, all of this data collection, and then also data distribution infrastructure. So your digital signs over the highways that are telling you how long it's going to get from point A to point B. Your roadside units. So with connected vehicles becoming more and more something that exists on the roads today, infrastructure is needed to communicate with those. So from the highway to your traveling vehicles. There are production cars out there today, your Teslas, your Cadillacs. There's a number of different production vehicles out there that can communicate with this infrastructure. We need to develop software to enable transportation agencies to propagate out the right data to those vehicles so that they can benefit from that technology. So the natural progression from these transportation management systems that just interfaced with existing devices on the highways was, well, we're a research and development organization, right? Southwest Research Organization is an interdisciplinary research and development organization. We work with all different disciplines, computer scientists, yes, engineers, chemists, across the board in many different industries we have involvement. One of the things we've done in the past and continue to do today is autonomous vehicles. A big part of autonomous vehicles is perception, being able to take inputs either from optical cameras or from LiDAR or any number of other sensors and turn that into something useful that the autonomous vehicle can then use to navigate. Turns out that same capability, those same technologies can then be applied to traffic camera feeds. These feeds that have traditionally been sitting manually observed by operators and used to try and identify actionable data. So is there a stalled vehicle on the roadway? Is there a wrong way driver on the roadway? All these things that's information that these agencies want to know about so they can do something about it. They can dispatch support trucks if there's a stalled vehicle that needs a jump start or a gallon of gas. They can dispatch police if there's a wrong way driver, or dispatch, more importantly, ways to notify the traveling public that there's someone going the wrong way down the roadway. It turns out seconds really do matter, especially in instances like that where 30 seconds difference is the difference between someone dying or not. And so if we can develop technology that is more effective at communicating that quickly and getting the right people out there to address it, we can save lives. This is really applicable, especially in the climate today, where at the national, state, and local level, there is a push toward Vision Zero. This is a vision throughout the transportation industry that looks to reduce the number of fatalities on roadways to zero. It's a big ask. I don't know if you've seen the traffic signs over the highways, but there's a rolling counter in Texas of how many deaths have occurred on the highways. It's certainly not zero yet, and that's just Texas. There's a long way to go, and technology is the only way to move that forward, and this, we believe, is one component of that technology that's needed. So at the 50,000 foot view, what are we proposing to do? We need to apply existing algorithms to kind of get our base information out of these video streams, and from there we can do more interesting high-level functionality. We can implement these things that the agencies need. So first of all, we need to collect a traffic camera feed. These cameras already expose feeds. That's how these operators have been viewing them forever. Easy enough to consume that. What we want to do next is identify all the objects that are present in a given frame within that feed, and then we want to track those objects as they progress throughout time. Once you have that base level information of the trajectory of each of the objects traveling, whether it be vehicles, pedestrians, or anything else of interest, you can then do really all of these interesting things along the right. So you can identify wrong-way drivers if you know the correct direction of the lanes that are in view and you know the direction that the vehicle that's traveling on it is going in. You can identify stalled vehicles when you identify a vehicle that's not moving. You can identify vehicle speeds if you know the physical distance being traveled and the time it takes for the vehicle to travel across that distance in the feed. All these things can be inferred based on this low-level functionality we see in the middle. So now we're going to talk about machine learning.
All right, so most of what we are going to talk about and what we did involves a lot of machine learning. So I'm just going to talk a little bit about it and so you can have some familiarity with it in case you've never heard about it or haven't done any of it before. More specifically, I'm going to talk about supervised learning, which is a subset of machine learning. Machine learning is very broad, and this is really only one small part. Something that you generally do in supervised learning is you create a neural network to accomplish a specific task. You use data to train that network and the way that it's to train that network. One task you might have a network do is take in a bunch of images with numbers drawn on those images and ask it to output what number is actually on this image. The way it's trained is by data being passed in and compared with the correct label, what the expected output of that network is, and it'll correct itself over time. So that being said, from start to finish, if you're just starting from scratch, you need to have all this data for the network. You need to collect all the data that you're going to use to train your model up and use it. Once you have all of your data, you have to label it. It has to know what the correct output's going to be. So if you don't have some other data set you got to use, guess who gets to label it? You do. After all that's done, after all the fun part's over with, now the actual fun part happens. You get to design your network and you get to train it and to accomplish the goal that you have set for it. But what is a neural network? Simply put, a neural network is just it's modeled after a brain, and it consists of a sequence of nodes that data passes through and mathematical operations operate on the data until it outputs the result. At each stage in the network, there's a sequence of layers consisting of nodes. Each node takes in input and outputs something different. In the main part of the node, the input is added together in the weighted sum, and it's passed through an activation function, and the output of that function is then output to the next step. Before it gets to the node, it has to be multiplied against different weights and added together. That's what the weights are. When you look at the graph of a neural network, like on the right, the edges of the graph are the weights that the data is multiplied against and are input to the nodes. The weights are actually what you train on your network. Those are what change in each iteration. There are many different kinds of neural networks, and some of them can get really, really complicated. Two of the most common types are convolutional networks and recurrent neural networks. Convolutional networks are expected to handle large amounts of data and are mainly used for images, and you'll use them quite often, and that's what we use a lot of. The one we didn't use, but you may see a lot, is recurrent neural networks, and those are used for processes that have multiple steps, where the results of one step affect the next step, and that has memory. So the data is taken from one step and applied to the next. Okay, now we're going to talk about what we did. First part is data collection. We collected two different main types of data, snapshots and videos. Where did we get this data from? Who did we get it from? Well, because of our close relationship with transportation, we talked to several different states and municipalities to get permission to get snapshots, video, and weather sensor data. Each district had its own unique infrastructure, so for each place, we had to have our own unique system of collecting different types of data that they may provide. Once we have this data, we have to have an infrastructure for storing the data. So we set up an old workstation with 4 10-terabyte drives, and we used RAID 5 to have fault tolerance in case some of the data got corrupted. That way we wouldn't lose all the data we collected. We were able to communicate easily with this workstation because our network was so quick. We didn't have to worry about that as to be an issue. On top of all that, when we wanted to set up some new system or some new device to talk to the different machines or run a different process, we had a strong virtualized infrastructure we could utilize and take advantage of. So how specifically did we collect the data? To collect snapshot data, we set up several different Windows services in C# that would receive the snapshots and then write the data to a server. At the same time, we would store the location of those snapshots as well as the time it was taken into a database that we could reference later. Some of these states also had weather sensor data, so at the same time the snapshot was taken, we would be able to learn some information of such as the weather and the visibility of at that point in time, and we stored that. Just to show how each place had a unique way of collecting data, for one DOT, we had to send a box over there that would collect the data and then send the data over the internet to an endpoint that we had open as a web service and then stored in our system. For videos, we collected multiple different video streams. In order to facilitate that, we created a multi-threaded PowerShell script where each thread collected data from a different stream. We used FFmpeg to receive the data and write it. But on top of all that, we couldn't just have FFmpeg running on and on forever. If that happened, we would have an infinitely long video, we wouldn't be able to open it, and if the video got corrupted, that's it, we lost all our data. So we set up FFmpeg to run for a configurable period of time. After that period of time, it would stop and we would restart it again to run so that we would have a sequence of small bits of video. That way, if something bad happened, we didn't lose everything. Now that we've collected all our data, we get to go on to the most fun part of the process. That's very sarcastic. We get to label our data. Most data labeling is manual. There's not really any automated way to do it all, because if you did, why were we doing this? Even if you have some way of having somebody else do it or some other automated system, it still needs some ground truth labels. For snapshots, we manually labeled all of our snapshots. For each snapshot, we wanted to determine the weather and the visibility. In order to accomplish that, we set up an HTML5 front end that talked to a C# backend that in turn communicated with the server the snapshots were on and a PostgreSQL database. So when we wanted snapshots to label, we would use the data in the database to find images based off the day, the time, and the location. We would then take those snapshots, label them, and the labels would be sent back to the database. On top of all that, we want to label some images for a rainy day. Well, you find out as you're labeling images over and over again that they're almost all clear skies. It's kind of hard to find a rainy day. So how do you do that? We had, on the far right and the bottom, you can see a graph of sensor data that we had received. This sensor data can tell us if it's raining in a specific time in a specific location. We use this sensor data to find images that were at the same time in the same location and have more rainy day images. That way our data set wasn't entirely biased towards clear days. Labeling videos was a little bit easier. We had all these video streams, but fortunately OpenCV, which is a computer vision tool, library that is very popular and you can use very easily in Python or C++, they have this tool CVAT that you can use. And now in CVAT, you can load up your video, you can select a frame, and draw bounding boxes around the objects you want. In our case, we wanted to draw bounding boxes around cars. You draw bounding boxes and labels, say if it's a motorcycle or a bus versus a car, and then you can skip forward a whole bunch of frames, and the bounding boxes are still there. You can move them to where the vehicles are now. Now every frame in between, CVAT will interpolate where the bounding box is. That way you don't have to do all of them by hand, because that would be extremely time-consuming and mind-numbing. If you want to look at CVAT, you can find it online at GitHub. Okay, well, manually labeling all of our data is not really something we want to do, and it's really not very cost-effective for us. So we utilized AWS's SageMaker to do that. AWS has this Mechanical Turk workforce that consists of a group of individuals that are incentivized to label your images by being paid a fraction of a cent per image. One big issue with this is there's no managers, there's no recourse. If there's bad labeling, there's nothing you can do. You can't say, hey, you're doing it wrong. You can give them some instructions, tell them what's a good image, what's a bad image, but you can't really, there's nothing you can do. They can still give you bad data. So we ended up using a private firm that had managers and that we could talk to that, while not affiliated with AWS, still used SageMaker and labeled a whole bunch of data for us. This helped us to later on train our models to be more accurate, while we didn't have to sit in front of a computer for weeks and weeks labeling. They had more people, and it was more cost effective for us. Okay, so we've labeled our data. Now we get to do the machine learning part of it. We get to do the fun part. We had two main parts of our machine learning. The one part involved weather detection, and the other part, which is actually, that together is object detection and then tracking objects in a video. So the weather detection was taking in a bunch of snapshots and determining the weather and the visibility. That's just a labeling task. What's best suited for this labeling task? A convolutional neural network. We created a convolutional neural net for each task that we had, consisting of convolutional layers, some dense layers, and max pooling layers, and then trained them on the data we manually labeled. So if you look at the image, we have that it would go through the weather net, the visibility net, and the snow network. But what's odd about that? There's a separate network for snow. The reason for that is DOTs often want to know, hey, is there snow on the ground or is there snow on the road? If there's snow on the road, they have to go pick up that and clean out that snow because that's a road hazard. But the weather network wasn't really well suited for that. So we created a separate network, snow, to detect on ground or on road. Now on to the object detection. For object detected, we used SSD, single shot detection. Single shot detection, you put an image into the network and it'll detect all the bounding boxes and classify everything in that image in a single pass. This is really unique because most other systems require multiple passes through a network and are actually much less accurate. On top of, so this also gives us the advantage that we don't have to do it over and over again. It's way faster. It accomplishes that through modifying a multi-box regression technique to detect the bounding boxes and then passing it through a detector to classify them. Now, to train this up from scratch would mean a lot of data, but there's some stuff we can use to make it easier on ourselves. We took this network and we used weights that were pre-trained on the Pascal and Coco data set. Now they might not be perfect for the vehicles we wanted to detect, like buses or cars. They might not be perfect for that, but that's a lot better than starting from scratch, and we just fine-tuned it based off of the data set that we had. If you look here, this is an example output of SSD. This image is actually really, really small, and SSD is not none of the detection techniques work really well for really small things. You see the cars in the back. The human eye can't even see that on the raw image sometimes. But in all honesty, it does a really good job for its task. Okay. So now you've gotten all these bounding boxes and all these frames, but how do you track it across a video? That's where deep sort comes in, or this simple online and real-time tracking with a deep association metric. Deep sort. Deep sort takes in detections or the bounding boxes in a frame as well as a frame, and it gives them IDs, or it gives an ID from a previous frame so that you are able to track it across multiple different frames. How does it do this? It's actually a two-step process, deep and sort. The deep portion involves a feature extractor, which is just a neural network that outputs a vector of descriptive numerical values about that image, just what's in the bounding box. So it'll have a different vector for a red car versus a white car. And this allows the network to differentiate between different objects so that later on, as time is going on, if a vehicle disappears, say, behind an 18-wheeler, when it comes out again, Deep Sort's able to say, hey, I've seen this before. I can use this one. It's the same one. And it provides the same label rather than using a new label. How did we do this? So that again? So we want to know what type of vehicle we have, and we want to know an ID, so we know that it's the same vehicle over time. So SSD determines the type of vehicle, if it's a car or a bus, and Deep Sort really just makes sure it's the same vehicle over time. So that's an ID. It's just 29, 29, 29. It looks like, hey, to the human eye, it's a video, but it's a lot more difficult for a computer to understand it, so we need an algorithm to track it over time. Say if the paths cross or something, then normally a computer might switch up the IDs and get confused, and that's where this feature extractor also comes in to make sure that they're the same. The feature extractor is just a neural network with an output vector. The network is really just like a classification network, except the labels are an ID of an individual vehicle. So we have a bunch of images of a bunch of different vehicles, and the ID of the vehicle is the vehicle itself. So it's trained specifically on the features of that vehicle, yes.
So in concept, yes, that is something that could be done. In practice, it's not something we're attempting to do.
Yeah.
There hasn't been a use case where it would be valuable to track a vehicle beyond the view of the camera. So we're driven by industry need is how we decide what to pursue, and there hasn't necessarily been interest for that yet. It's not to say there wouldn't be. For example, if you've got a wrong-way driver that occurs in front of one camera and then it drives far enough that it's no longer in view of that camera, one could see an argument for trying to then go and continue watching that same vehicle on whatever the downstream camera was.
Theoretically, you can. We can't right now.
We have not tried to.
Yeah. After we've got all this feature information about that individual vehicle, we just perform a sequence of mathematical operations in the sort portion that include a Kalman filter, an assignment algorithm, and a distance metric. Sort is actually a separate thing that's used for tracking across frames, but the deep portion helps make it more accurate and track better, honestly.
All right. So computer vision is about more than just machine learning, so we're going to touch a little bit on what that extra part beyond machine learning looks like in this particular instance. So we're going to look at lane learning. It turns out in order to accurately detect wrong-way drivers, you have to know what the correct direction for that vehicle to be traveling is before you can determine if it's going the wrong way. We've already talked about how you determine what direction a given vehicle is traveling. But how do I know if that's wrong or right? lane learning is how you get there. So over time, you can observe the trajectories of each vehicle that travels along a given segment of road. This particular screenshot here is off of a video that we took of an intersection actually on the Southwest Research Institute campus. We've got a traffic camera sitting up there that allows us to readily collect data and break a few traffic laws when we need to, which you'll see in a minute. But by viewing this pattern of trajectories of vehicles over time, we can learn with varying levels of confidence, depending on how much data we collect, where the lanes exist. So if you look here, and you can't really see here, but each of these actually has a point on the end. It indicates the direction that that vehicle was traveling. So each of those lines is actually an arrow. If you have a clustering of arrows in a dark section, that means you've had a ton of vehicles travel down that space, and you can infer that that is in fact a line. You've got a gap in the middle between the two lanes showing that generally you don't have people driving down the median. And then you've got a different color arrow, and those arrows are actually pointing in the opposite direction, indicating that vehicles were going in the opposite direction. So from all of this, you can come up with something like this. Basically a way to notate that I believe that these are lanes based on purely the observation of vehicle movement. So we don't attempt to read the stripes on the roads because the amount of variability between different agencies, different countries, everything else, that what a lane looks like visually differs so much that we did not believe that would be a viable option for a portable solution that could be applied everywhere. But you can track vehicles no matter what you're looking at. And vehicles tend to generally stay within lanes as long as you remove outliers along the way. So then we applied this. So this is the same video that built that arrow map, and you can see it getting generated in high speed. This is over about 30 minutes worth of collecting data at that intersection. And then you'll see coming up here after a while on your left, that traffic law that I was mentioning. So we got a pickup driving the wrong way down that intersection, and obviously this could have been faked. I promise it wasn't. So we correctly identified very shortly after it entered into that frame of view, once it was able to get a trajectory, that it was in conflict with the correct trajectory of that lane that we'd identified previously. And so it boxed it in red, and then for emphasis, we've got the flashing red there. So that's all well and good, but we're an applied research and development organization. At the end of the day, we need to have something that can be applied to real-world needs. And so our clients, transportation agencies, need to be able to put this in production somehow. And so we spent a fair amount of time looking at the various ways that it would make sense to deploy based on the infrastructure that they have available and based on the infrastructure we need in order to run the algorithms that are relevant to this detection. So we looked at 3 different options. The first is edge deployment. So in this case, you've got your compute sitting in a cabinet directly alongside your cameras, and it is processing those feeds, and it is generating detections without traveling over any network other than whatever short connection there is between the camera up on the pole and the compute down in the cabinet. From there, if you've got edge connected devices like signs up over the highways or roadside units, which we talked about earlier, that will communicate with your connected vehicles without ever needing to send network traffic anywhere else, without reliance on your cell modems to be up or your fiber to not be severed or a tornado not to have run through like it did in Nashville just a couple days ago. If you want to be absolutely certain that you're going to have connectivity between these devices, that's the best way to do it. It also comes at a cost. You've got to now maintain each of these edge compute devices and replace them periodically, and that distributed nature inherently adds cost. It also caps the amount of compute you can reasonably have. We've been using the NVIDIA TX2 chips, which are system-on-a-chip kind of systems that have a GPU on board, so they have pretty significant capabilities, but they are still limited. It's ARM processor-based, which has some challenges of its own compared to targeting Intel-based systems. The next option is the Traffic Management Center. So has anyone heard of TransGuide? Okay. Yeah, if you watch the local news, you've probably seen the traffic camera feeds from TransGuide. That's the local TxDOT office for San Antonio, and we do a lot of work with them. And this is actually a photo of TransGuide's Traffic Management Center. But in each of these centers, they generally have some amount of rack-mounted compute. That's where our advanced traffic management systems are running, for example. There is compute capacity there that can be leveraged as long as you have the bandwidth availability between the field where the traffic camera is deployed and the TMC in order to get those things streaming constantly. If you can do that, you can do detections in a centralized location. The cost of compute goes down. And finally, I know y'all are talking about using cloud hosting for Rowdy Hacks, which we're excited about coming to join y'all for in a little bit here. We also looked at cloud deployments here, because the reality is across industries, companies are looking more and more at not using physical on-site infrastructure. The cost both of manpower and of the replacement cycle for this hardware, which production hardware, every 3 to 5 years, you need to be throwing it away and getting new hardware. That's a lot of expense that can be consumed at scale by a cloud provider that will bury all those costs for you and be able to charge less than what it would cost you to do it yourself. So we also looked at the implications of deploying in the cloud and what would be needed there. And of course, at that point, you need bandwidth capability, not just to the traffic management center from the cameras, but also up to the cloud as well, to the public internet. And so the implications there and whether or not that's feasible for the agency. The right choice is going to vary based on who the agency is, what their on-site compute capacity is, and what their requirements are for the deployment. So I mentioned there's some complications depending on which of these we select. With the edge deployment, the most complicated part of that is we have to target ARM architecture. And I don't know if any of y'all have tried to do that before. It's a pain. Most of your off-the-shelf compiled binaries are not ready for ARM processors, and so you're building everything from scratch, from FFmpeg to TensorFlow to all of your .NET bytecode. Everything you've got to target ARM, which can be done. It's all doable, and we're doing it, but it's a pain. So that's a challenge that we're working through right now. With the Traffic Management Center, everything is pretty much kind of your standard. It's the way we've been doing things for decades at this point, so it's not too challenging for us. On the other side of things, the cloud hosting. Looking at how we can leverage the technologies available in a cloud hosting environment to maximize our compute per dollar, right? So if you can look at serverless technologies where you don't have dedicated compute sitting there constantly but only spun up as needed, conceptually you can reduce the total cost of running the system. It also provides effectively infinite scalability, which is also nice and means you don't have to go spin up new VMs each time you bring more streams online. All that just transparently kind of happens, which is nice. And so the end result, and this is a diagram our media people put together that kind of shows the pipeline of what this would look like in a production environment. So in the field, you're collecting video feeds. It gets processed by this computer vision technology, which we're calling active vision, either on the edge or in the traffic management center or in the cloud. Doesn't matter for the purposes of this. But then the detections that are coming out of that, the actionable data, is consumed by your advanced traffic management centers, by internal systems. You can send out emails to relevant parties when things happen. You can dispatch police based on wrong-way drivers. All this data can be used to inform decision making. And so what the agency chooses to do with that is up to them, but our goal is to make that data available without the need for manual observation. And so with that, we can take questions. There's no way y'all don't have questions. That's not possible. Yeah. Ongoing. No, so Sabrina and I were working on the weather detection stuff. We started that 2 years ago. And so that was the first internal research program that was funded to do this. Relatively low dollar amount compared to the current research program we're working on now that's looking at the more traffic-based detection, so the things that are considering vehicles, whereas in weather detection, vehicles weren't relevant to whether it was raining or not. And so it's ongoing, and we've got about a year left in this current research program, and we expect to do continuing follow-on work just as our customers show interest in different components and their needs to explore those options. Yeah, gentleman in the front, and then in the back, and then you. Yes, yeah. Unfortunately, so not universally throughout Southwest Research, but for all of our computer science positions. So we, as an organization, do a lot of secret and top secret work that just for federal reasons we can't hire internationally, which is really unfortunate. But it's the nature of what it is, yeah, sorry. Yeah. So the object tracking we're using there is only considering vehicles. So it's the assumption is that they're generally on the roads. We do also have some logic in there that's removing outliers. So if you had someone, kind of do a S-curve through the center, that would be deviant enough from the expected patterns that it would get weeded out and not considered when we're looking at figuring out where those lanes exist. Right. And that was one of the big requirements when we first started looking at this work was these cameras are being used. They're primarily movable, right? They're pointing at different stuff. We did not want a requirement for using this to be, all right, you got to stop using your camera now. And so basically wherever it's pointed, the intention is that we be able to operate on whatever's in view. Obviously, if something's not in view, then there's nothing we can do about that. But if the road's in view, we want to be able to operate on that. You, and then back to you. It was a little of both. So what it started out with was requirements, right? So it's with pretty much everything we do, it's requirements driven. So we need to figure out what it is we need on the other end of this, and then we kind of work backwards from there. So for that initial program where it was just weather detection, initially it was actually just visibility detection, and we achieved that so quickly and with so little of the allocated budget that we added scope to do weather detection, picking up snow and rain and all these other things because that was more interesting and we had the budget to do it. But the requirements started off as we need to be able to detect basically within bins is the visibility, less than 500 meters between this range and this, and basically accurately be able to represent that because we knew that that was a need that our customers had, and so we wanted to get to that point where we could deliver something that would be of value to them. And there was another part to your question, right? Or is that? Okay, all right, cool. Yeah. Mm-hmm. Yeah, I didn't quite catch that. What are the differences? So, yeah, so you're talking about the training side of things or the running the completed models? So the training actually only ever occurred on static images. In some cases, we would use sequential static images from a video, and that was useful on the deep sort side of things. I don't know, Sabrina, if you want to.
The feature extractor, the IDs for an individual, the IDs for, with the feature extractor, the ID for an input would be just each vehicle had its own unique ID. So in order to train it to label the same ID, you had to have multiple images of the same vehicle. The best way to do that is to have sequential images, so that's where the video is most helpful. On top of that, you have so many images you gotta label and draw bounding boxes along. It's a lot easier to do that in a video than to do that over 100 random images.
Yeah.
We have a question from the stream. What infrastructure exists that notifies local first responders when a vehicle is going the wrong way?
So that's a great question. There are some dedicated hardware solutions out there. Various vendors have built physical systems, often LiDAR or infrared based, that will detect vehicles that are going the incorrect way, generally deployed in very isolated environments because they're pretty expensive, often on ramps where there's a known pattern of this occurring regularly, so potentially around bars or things of that nature. Most of the time, wrong way drivers happen at night. And then for obvious reasons, both because of visibility and because people traveling at night are often potentially intoxicated. So those solutions exist out there. They're very expensive. And so one of the big arguments for this solution is you can reuse that existing camera infrastructure that has already been paid for and deployed and being used, rather than needing to go buy new physical infrastructure to support detecting wrong way drivers.
Thank you.
Yeah. Sure. So there are multiple angles to go from. There's one side of it is, yes, dispatching police or whatever else. Often that's going to inherently just be too slow. The reality is the time it takes for someone to receive that call, drive from wherever they're at, unless they're sitting on the highway, half a mile up, it's unlikely that they're going to be able to get there in time. What is more realistic, I believe, based on where the industry is going and what technologies are out there, is getting better about propagating the knowledge that a wrong-way driver exists to other drivers on the roads. So that can be done through connected vehicles where, say, on your dash, the infrastructure broadcasts a message that says there's a wrong-way driver up ahead, get off the road. Or on the traffic camera, not traffic cameras, on the traffic signs overhead, you have messages, big, bold, flashing, you're driving the wrong way. So technology-driven rather than person-driven is likely the only way to get close to 0% fatalities out of those, because if you do have a head-on collision between a wrong-way driver and a right-way driver, it's the percentages for fatality on those, and you can pull up the numbers. These are public information from the Federal Highway Administration. The numbers are not good compared to a standard collision where you're not going head-on. They're very bad. So then you're reliant on infrastructure-based communication. So like those signs overhead that can display that information. Obviously, then you're reliant on someone actually looking at those signs. I know I personally generally don't even look up at those signs unless I'm stuck in traffic, which is not super useful. So that's a challenge as well. So there's kind of a waiting game there for how long it takes for that penetration of connected vehicles to get a little more saturated. Yeah. Yeah, so in training our models, they're all based on, we've identified 9 classes, I think, total. I think it's 9 classes, because I know SageMaker caps at 10, and one of them was an ignore class. So it's 9 classes. Most of those classes are different kinds of vehicles. So your 18-wheelers, your pedestrian vehicle, your motorcycles, your bicycles, all this kind of stuff. And then as well pedestrians. And that was trained across our data set that covers all of the agencies that were partners. And so you got all kinds of different environments. So like New Mexico was one of our partners. The video feeds from there are, I don't know if you've seen photos of New Mexico, it looks very different. The land looks very different than it does, say, here. You've got a lot of orange sand and kinds of other stuff like that. And so the pictures are all very varied in what they look like. You've got snow in some pictures. And so the goal was to diversify that environment as much as possible to really train a robust model that was capable of identifying these vehicles regardless of what environment they were found in. Yeah.
I know you mentioned that when you had to train systems, train them from the ground up was going to take a lot of data and time that you didn't have. How far could your data set actually?
So we ended up, the number of images we have total versus the number of labeled is a vastly different number. We have many terabytes of images. We have certainly not labeled them all. For the vehicle detection, we labeled 25,500 images total. And I don't know how many individual objects were identified throughout there. I don't know that we ever actually looked at what exactly that number was. And so varying numbers of the different classes, we had varying numbers that we were able to identify. And there's certainly work to be done there in terms of fleshing out some of the harder classes to find. So if you think about it, how many motorcycles do you see on the road versus your standard commuter cars? And so getting enough data to have a model that can capably identify those is hard, and we haven't solved it yet. We're working towards it. That's why we got a year left.
Collecting more data, labeling more data, and then tweaking your network based off of the data you have.
And you say images, do you mean like just flat JPEG PNG, or do you mean like actual video?
Just flat JPEG PNG.
Yeah. Yeah, so FFmpeg, we'll use it to pull out individual frames from a video. So basically, we've got a little script that Sabrina put together that goes and picks a random starting point throughout these 2-hour videos and pulls an arbitrary number of frames that are sequential that we can then use to label, and so we get a nice data set throughout all of our videos. I saw a question in the back.
Are you all currently working on any inter-vehicle communication, such as cars being able to warn each other if there is a wrong-way driver?
Yes. So that's in another department that we work very closely with, but we do a lot of work with both vehicle to infrastructure and vehicle to vehicle communications. A lot of that work is done with OEMs, so the car manufacturers, and helping them both identify what the standards need to be and sitting on the standards committees that define how those vehicles need to be communicating with each other so that everyone can be on the same page. Because ideally, you don't want, all right, I'm a Cadillac, all my other Cadillac people can talk to me, but I can't talk to any of the Teslas, I can't talk to any of the Fords. So you want to have a standard that allows all these vehicles to interoperate, because otherwise the value proposition for vehicles being able to communicate with each other is drastically limited. So yeah, we're certainly involved both on the standards side, also on the certification side, confirming that these car manufacturers are complying with whatever standards exist, and then also helping design the standards as this field is emerging. It's still definitely in its infancy in terms of connected vehicles and what the possibilities are, and things like 5G and DSRC and the battles that exist there in terms of what network is going to carry this massive amount of data that's going to have to exist in order to communicate between each other. All those things aren't solved yet, and so the industry is still figuring a lot of that out. I don't know who's first. Okay, yeah. Any projects that we're working on? Sure. Yeah. At any given time, I think what's the number right now? I think we claim we've got 10,000 active projects at any given time. I think that, don't quote me on that, but it's in the many thousands of active projects. Some are small, some are big, some are internally funded, some are commercially funded, some are government funded. We've actually got an exciting project right now. We're working with the city of San Antonio to actually deploy this technology on traffic cameras throughout the city, and so it's part of their R&D league. It's on the internet. You can find references to all that and what they're doing, but they're basically partnering with a bunch of agencies throughout the city, including UTSA actually, and doing different interesting things to try and help the efficiencies of the city and allow the city to kind of leverage technology that historically they haven't considered. So that's one. All of those logos you saw at the beginning are different, with the exception of San Antonio. Those all represent advanced traffic management systems that we're developing and supporting. We're doing stuff with San Antonio as well. It's not a transportation management system, but it's other things related to that.
Our division alone has autonomous vehicles and cybersecurity, as well as transportation. There's robotics. There's a lot of stuff in our division alone. I know a guy in a different division that does stuff machine learning related to airplanes. So it's anything you want, they have. Yes.
We are. Yeah, no, if y'all are interested, we've both got business cards, and definitely reach out to us and we can give you more information. Our employment opportunities are always at swri.jobs. So you will see us at Rowdy Hacks and everything else, so we'll be happy to repeat that as many times as it takes to get y'all to apply, but we're actively searching both for interns and full-time positions. So if you're interested, we'd love to have you. I think I saw another, okay, yeah. Oh, okay.
If you got to go to class, go to class. Will you guys be able to stick around for questions and stuff like that? So
Absolutely.
Dan and Sabrina will be here, but there's pizza in the back if you want to go out that way.
Yes, eat pizza. We don't want to take it with us. Yeah, absolutely.